And then just give a few minutes for all the attendees to filter in. So welcome everyone. We'll just give a few moments for people to join before we get started. Okay, well, we'll get started, and if anyone joins late, they can catch up, I'm sure. It's my very great pleasure to introduce Aaron, a senior lecturer at the University of Lincoln. Aaron was one of the very first Catalysis Hub postdocs and has gone on to great things. And here he is to talk about some of his work on the absorption of atoms and molecules on catalyst surfaces. I'll hand straight over to Aaron.
Thank you, Josie. Thank you so much for the kind intro. Let me first also thank the UK Catalysis Hub for kindly giving me this opportunity to interact with you. Now, as the title of this presentation suggests, today I'm going to talk about the adsorption of atoms and molecules on catalyst surfaces, of surfaces in general. Now, at this moment, perhaps you are wondering, why am I interested with the adsorption properties of atoms and molecules? Well, the studies on adsorption is not new. It has been around for quite a long time now. So as early as 1834, Michael Faraday, who is one of the most influencing and one of the most inspiring figures of chemistry, did some of the original studies on adsorption properties. Since then, we have come a long way. And as you all know, in 1916, Irving Langmuir did some of the fundamental studies in this area. At this moment, from our studies in physical chemistry, we already know that adsorption could be either physisorption, also known as chemisorption, physical adsorption, or van der Waals adsorption, or it could be also chemisorption. Now, the amount of heat released during physisorption is about 20 kilojoule per mole, which is very weak. And the chemisorption ranges between 100 to 500 kilojoule per mole. Now, the question is, why am I interested, right? So I'm interested with adsorption properties because it is one of the fundamental processes that takes place on the catalyst surface before the molecules dissociate, diffuse over the surface, recombine with the other adsorbed species to form the final product. And this is the reason why I'm very interested. Now, if we try to translate it into graphics, let us take an example. For example, here, the CO oxidation. What are the processes taking place here? So you can see the oxygen molecule, there's a gas phase diffusion, and then it is coming to the surface and adsorbing. So there is a molecular adsorption. Then this molecule adsorbed on the surface could dissociate. And so we can call it as a molecular dissociation. And then these atoms could diffuse on the surface, combined with the other molecules leading to the formation of carbon dioxide. Now, this whole process, we could write in the equation form as follows. So you can see first there's gas phase diffusion for both carbon monoxide and oxygen. And then there is molecular dissociation. And then there's a combination of these atoms and carbon monoxide, giving carbon dioxide. So you can see here that the adsorption process is very fundamental. So if we understand how molecules and atoms or atomic clusters adsorb on the surface, we'll get to know a lot of important information. And additionally, there very unique kind of phenomenon might be taking place at the interface between these adsorbed species and the surfaces. So today, my idea is to present two studies from my own research. One is the transition metal catalyst on oxide surfaces. So I'm going to present this as a tribute to the UK Catalysis Hub, where I studied chemistry for more than 4.5 years. I gained a lot of experience. So I thought it'll be a good idea and a good time to say thank you to the UK Catalysis Hub. And the second one is on the latest work that we have done at the University of Lincoln in collaboration with scientists at Brunel University and Gloucester University in Germany. So it'll be on the formation of porous polymer materials due to the self-assembly of benzene on the CO2 surface. Now, when I'm talking about the transient metal catalyst and oxide surfaces, so we have done quite a bit of work now on these, and I think a graphical abstract on the whole work would be quite informative here. So we have started from single atoms of gold and copper, and then we have built these clusters. And with time, we are building it bigger and bigger cluster and looking at the interaction of these clusters with the surfaces. And we have done this in presence of an absence and presence of water molecule. And also at this time, we're also looking into the interaction of certain molecules on these atomic clusters. So the story that I'm going to present here began sometimes in 2013 when I came to the UK Catalysis Hub somewhere here. And our experimental colleagues, they did some measurements at the diamond light source here. And then they say that they have some very interesting data on their copper catalyst. And I thought it'll be, they said that they have some information on the copper oxide catalyst on Syria. And those important data that they had were, for example, copper is in the 2+ oxidation state. Number two, the distance between the copper and oxygen, they have got two distances. One is 1.940 angstrom and another is 2.390 angstrom. And the third data that they had is that copper has an environment of oxygen with either distorted octahedral or square pyramidal environment. So our main idea was then to find out if we can reproduce or if we can model this catalyst that they have. So the objective of this study was to find out or to study the local geometrical and electronic properties of copper adatom and copper oxide clusters on the Syria surface. So to perform this study, we used density functional theory as implemented in VASP. And we use DFT plus U studies, the method here. And for our modeling part, we use the 110 surface of Syria. The reason being it is catalytically more active. So here I'm showing you the surface of Syria 110. Now for convenience of visibility, so I'm visualizing the uppermost layer in ball and stick form and the rest as CPK form. Now you can see that on the surface, basically, we can put these copper atoms in one of these 5 positions. One could be on top of the oxygen atom. The other could be on top of a cerium ion, or it could be in between the cerium and oxygen ions, or on the trifold side, or it could be in the long bridge side. Now, this is the top view, but if you look at the side view, then we can see that there are some ridges here. So we are calling that the oxygen atoms in between, this site as the long bridge site. So we begin our studies first with the single atom of copper. So after optimization, the molecule, the atom, copper atom, it moved to the long bridge site. In the second model, where we put the copper on top of a cerium ion, we could see that the distance between cerium ion and the copper ion, it moved away. So the distance was about 3.3 angstrom. At the same time, we did this calculation for all the models, and we found that when we put it on this oxygen and Syria bridge, it again moved to the long bridge site. Yeah, but the copper atom, it was on the same position after optimization when it was on the 4-fold site. Now, if we look at the adsorption energies, we'll see that actually when we put this copper ion on top of the cerium ion, then it is very weakly adsorbed. Yeah, there's physisorption. But in these cases, when it was on top of the oxygen atom that moved to the long bridge site, or when it was on the bridge site but moved to the long bridge site, they were having a very low adsorption energy, means copper ion was quite stable on these two models. Now then, there's an interesting question here. As you can see that the adsorption energies are slightly different, even though the copper ion is on the long bridge side. What is the reason? Why is it that in spite of their similar geometry, they have got slightly different adsorption energies? Now, we think it is because the way copper ion is making chemical bond with the nearest oxygen atom. To clarify this reason, we looked into the partial density states. So this is the partial density state for the copper S, copper P, copper D, and oxygen S and P orbital of the nearest oxygen. And overall, if we look at the partial density state, they look very similar. There was not much difference, but around -5 to -6 if something interesting we could see. And that is, in this case, there's not only the contribution of other orbital signatures for this model, but also there is a contribution of copper p orbital signature, which is absent in the other. And we believe this might be one of the reasons why one of the models have got lower adsorption energy than the rest. Now, having understood how the copper ion behaves on the Sirius surface, we wanted to know about the other interesting electronic properties. For example, electron transfer. Can we understand that? Now, to understand the electron transfer behavior, it'll be good if we first look at the electron configuration of the cerium atom. So in the cerium atom, we have got 4f1, 5d1, and 6s2 electron configuration, the valence shell electron configuration. Now, for the cerium ion on the Sirius surface, this is the electron configuration. So there are no electrons here. But when we see, if there's electron transfer from copper ion to copper atom to the cerium ion, that means it has gained an electron and it will go to the 4f orbital. So our new electron configuration will be 4f1, 5d0, 6s0. So if we look at the partial density states for the f orbital signatures, it will give us an idea whether there has been electron transfer or not. Let's have a look. So this is the partial density states for the f orbital signatures, and we can see a very big peak above the Fermi energy for the f orbitals. These are the unoccupied states, and there are no electrons here. But with the transfer electrons, we can see a tiny peak has arrived, has appeared just below the Fermi energy. This clearly shows that there is electron transfer, and one of the ions, cerium ions on the surface has been reduced to 3+. In addition to this, what we did, we analyzed the charges of all the atoms, and we found that the charge on the cerium ion before the copper adsorption was 2.385 electrons, but after they are reduced, it becomes 2.102. So it also clearly shows that a surface cerium ion has been reduced. Now, in addition to that, we also visualized the charge density difference, and which also clearly show that there is electron transfer. As you can see around copper, there is electron depletion, and we can see characteristic f orbital signatures, lobes of f orbital in one of the cerium ion, which means there is electron gain. So this is the side view, and this is the top view. Now, this particular study of atoms of copper on Sirius surface has obviously given us a lot of nice information about electron transfer, chemical bonding, and so on and so forth. But we were not able to reproduce the experimentally observed distorted octahedral or square pyramidal environment. Now, of course, when we look into the distance between oxygen and copper ions, we could see that we have reproduced one of the bond distances, but still we are far from what the experimental colleagues observed in their experimental measurements. So in the next step, we thought one idea could be that if we substitute one of the cerium ions with a copper ion and create an oxygen vacancy, this might give us some kind of idea that, if we could, we wanted to just see if it could reproduce the experimental observation. We did the same kind of calculation in the bulk as well. So we substituted one of the cerium ions with a copper ion, and then created an oxygen vacancy to give it a 2+ state. But in this case also we saw that while they form very strong chemical bond with nearby oxygen atoms, but it was not able to reproduce the octahedral geometry or square pyramidal geometry for the copper, or the oxygen environment for the copper. We also looked into the copper oxygen distance, and one of the copper oxygen distance was reproduced, but not two. And then we also analyzed the chemical bonding in these systems, and we found actually, as you can see around copper, we can clearly see the d orbital signatures here, and for the oxygen they're p orbitals. So there is a kind of chemical bond between them. It was also clear from this study. So while both studies, they gave us some ideas of how copper is behaving on the surface, we are still far from what experimental colleagues observed. So we thought in the next step, perhaps we can take clusters of copper oxide. So we began by taking copper oxide, copper and oxide dimers like this. So in this model, as you can see, we have put the copper on top of a cerium ion and the oxygen in the long bridge side. And in this one, we put the oxygen on top of a cerium ion on the surface and copper on the fourfold hollow site. And after optimization, we saw that actually, perhaps this is one of the models, reliable models that we could continue working on, perhaps by building the cluster of copper oxide and see if we could reproduce the experimentally observed coordination number as well as the bond distances. So to continue with that, we first build the first layer of copper oxide, and then we put a second layer of copper oxide on top of that one. While we were able to reproduce some of the bond lengths between copper and oxygen, but we can see that here in both the cases, copper still has an environment of 4 oxygen around it. So, we were not able to reproduce what experimental colleagues have observed. So we needed to do some more work on that. So we thought the best idea would be that if we speak to our collaborators and find out what was it, if they had water molecules in their system, or if there's moisture in the measurement when they did the measurement. So this might give us an idea. And they came out and say that yes, indeed, there is a possibility that there will be some kind of moisture in the environment. So to model that, we thought there could be two kinds of model. One would be that we put the copper on the long bridge site. So it'll have 4 oxygen around it. And then we bond it with 2 hydroxyl group, or we put 2 water molecules on this and find out how, if we can reproduce the experimental observations. So this was the first one. After relaxation, we saw that the copper ion has actually formed a square planar geometry as shown here. And in the second one, we saw that the copper has bonded with the surface oxygen, and one of the water molecules has adsorbed on the surface, and another one floated close to the copper. So we thought that this model could be quite reliable in extending this study and find out if we could reproduce what the experimental observations have been made. So we took this model and then we put water molecule around it. So we started with 1, 5, 10, 15 water molecules. And our calculation indeed showed that when we put 5 water molecule, it reproduced the experimental, the coordination number of 5. So you can see copper is having 4 oxygen here and another oxygen from the water molecule. Now, if we calculated this, when we calculated the bond distances between copper and oxygen, we found that actually on the surface, the bond distances were quite similar to what the experimental observations were made. One was 1.996, another was 2.307 angstrom. So from this, we concluded that the model with 5 water molecule best rationalizes the experimental data. And is consistent with the fact that excess data were measured on the catalyst exposed to atmosphere, probably having adsorbed water molecules on the surface. So this is one the very interesting study we performed at the UK Catalysis Hub. And if you'd be interested, please have a look at this paper published in 2017. Now, in addition to this transition metal catalyst on oxide surfaces, we have been also very interested in working with molecules. So the second story that I'm going to present today is about the formation of porous polymer materials due to the self-assembly of benzene on the copper oxide surface. Now, on the catalyst surface, we have worked on different kind of wide range of molecules. So if you'd be interested, please have a look at some of our papers which we published. But we are very interested with a simple molecule, for example, benzene. Now, over time, we have not only looked into how benzene can be reduced to cyclohexane through cyclohexadiene 1,3 and 1,4, cyclohexene and cyclohexane, but also we are looking into some complex molecules like these. Perhaps you are wondering, why is it that we are interested with this kind of molecules? The reason is that we want to model very complex carbon materials, especially amorphous carbon materials. And we thought that understanding how these simple molecules behave on the catalyst surface would give us an idea how metal catalyst behaves on these complex amorphous carbon. So this is the reason why we started this particular work. We have been also working on other molecules like furfural, and these studies have been in collaboration with scientists at ICIS Neutron Source and University of Milan. But today, I'm going to present, as I said, a study on the self-assembly of benzene, which I have done with one of my collaborators at the Brunel University and scientists at the Clausthal University in Germany. So first, I will present here some experimental and theoretical data, followed by the theoretical data on the self-assembly of benzene. But then the first question that comes to our mind is, what is self-assembly? Well, self-assembly of molecule occurs when molecule form an assembly of larger size, structures, spontaneous manner. And there are a lot of examples, biological examples, for example, ribosome from proteins and RNA and so on and so forth. And but then we are in this work, we're interested how benzene basically self-assemble, and why do they self-assemble. So these are some of the questions we wanted to answer. So the story began with some experimental measurements done on copper and copper oxide, experimental studies on the electropolymerization of benzene. So the experimental colleagues, they found that when they measured the electropolymerization of benzene, they saw they found that it commences at around 1.75 volts. Very, nicely it can be seen here. Now, when they performed this experiment with, platinum and gold, similar behavior was observed. But in the case of copper oxide, they found that actually there are two peaks, and one peak starts at around 1.3 volt to 1.5 volt. And another peak is 1.75 volt, which is similar to what they observed in copper or platinum or gold. So they repeated this experiment several times, and they observed the same phenomenon again and again. So it means that the presence of the oxygen on copper is perhaps responsible for the occurrence of the second peak here somewhere. And the oxygen is playing some kind of interesting role in the electropolymerization of benzene. They performed further experiments with SEM and FTIR, and this is what they observed on copper surface, and this is what they observed on copper oxide surfaces at different time. Clearly, they could see some porous materials being formed on the copper oxide here as compared to copper. Now, in the 80s, there were some studies which talked about the degree of polymerization, which they found when they took the ratio of the CH bond vibration of the polymer and the monomer CH bond vibration. So this, they say, it give a degree of polymerization. Now, my experimental colleagues, they performed this experiment and found the degree of polymerization on these different systems they did. And they found that, for example, in platinum, it was 14, gold, it was 17, copper, it was 22. For the copper oxide, it was 25. Again, it showed a very interesting behavior on this. In addition to this, characterization, they also performed some experiment with XPS. Now, these are the XPS data for copper, and this is for the copper oxide. So we can clearly see the differences between these two surfaces. In the first one, they can see some shake-up satellite peaks, which were because of the pi-pi star transition, but these were quite weak here in the case of copper oxide. Additionally, they also found some, a solder in the in this experiment here, around here, which we believe is because of the ionic liquid present there, but which was also absent in this case. And the main peak is because of the CC bonds at around 284.8 electron volts. So now these experiments, SEM, FTIR, XPS, I'm not an experimentalist, but these studies have clearly shown that there is a very different kind of electropolymerization mechanism for copper and copper oxide. So if you want to know more about the experimental details, please look at our paper, which I will cite later. Now, the questions that we wanted to ask from these are like, why benzene self-assembles on copper oxide surface? What is the reason behind it? The related questions associated with this is, how is the interaction of benzene different on the copper oxide, copper 111 and copper oxide 111 surface? What's the reason? Yeah. Now, also, when we have got one benzene already adsorbed on the copper oxide surface, how would the second or the third benzene behave? So these are some of the questions that we thought would be interesting to look at when we perform this study. Now, to perform the theoretical calculation, I again used periodic density functional theory calculations, which are as implemented in VESP. And we used these 111 surface for copper and copper oxide. And because we are working with this organic molecule, the dispersion effect might be very important. So we took into effect of the dispersion effects by D3 correction of Gramy. And because we adsorb our molecule only on the exposed surfaces, so we thought to take into account the spurious dipole moment, we considered the Markov and the Neubauer algorithms as implemented in VESP. And let us then see what we found from this study. So first of all, we performed the calculations on benzene adsorbed on different sites over the copper surface. But after adsorption, we found that they have got all similar geometries. Calculated adsorption energy showed that benzene is actually weakly adsorbed on the copper surface. We said this kind of these structures that we obtain as half and half geometries. The reason being, as you can see, half of the carbon atoms of benzene are on top of the copper atom, and half of them are on the threefold hollow site. And this is similar, consistent with all the models. And we found that the distance between the benzene and the copper surface is approximately 2.83 angstrom. And another interesting point is that the benzene molecule remained planar to the, it did not lose its planarity. It was not distorted or buckled. So this is one interesting feature we found. We repeated the same calculation in the case of copper oxide as well. So what we did, we again scanned, we put the benzene on different sites and then performed these calculations. And we found that the benzene ring in the case of copper oxide are quite strongly bound to the surface. Yeah, and the distance is, of course, in this case, 2.252 angstrom. And again, we did not observe any kind of distortion. But this is the top view of our model. If we see it from the side view, then we see something interesting, and that is the molecule, the benzene molecule has a slanted geometry. It's not planar like the previous one, but it's slanted. So now let us compare this geometry side by side and see how the benzene ring or the benzene molecule behaves differently on copper and copper oxide. So this is our models. Yeah, in both the cases, as you can see, the benzene molecule retains its planarity, but in this case, it has a slanted geometry, but in this case, it's parallel. So the first question is, why is it that here the benzene has attained a slanted geometry? What is the reason behind it? Well, the probable region perhaps lies on the, we can understand it if we calculate the charge on this system. So our charge analysis show that the copper oxide surface, it has centers of positively charged and negatively charged ions. So oxygens are slightly negatively charged and the copper ions are positively charged. And there's a residual charge on the benzene ring, which is about minus 0.054 electrons. So this benzene ring, because of its charge, negative charge, this is slightly repelled by the charged centers and attracted by the positively charged copper ions. And because of this, they have got a slanted geometry. And we have seen similar kind of very interesting geometries when we did study the other cyclic materials on other surfaces like nickel oxide, for example. So this analysis clearly show the reason why, this molecule is slanted while this is parallel. Perhaps, in addition to that, we looked into the charge density difference between these molecules, and this is what we saw. In this case, we found that the electron charge density is localized only on the benzene ring. In this case, we can also find that there's charge density between the benzene ring and the copper oxide surface. Clearly, there is a strong chemical bond between this molecule and this surface. Now, there could be another way to look into it is to draw this in 2 dimensions. Yeah. So if we look at that, then we'll see this is 2-dimensional charge density difference, planar average. So this, the positive side gives us the bonding region and the negative side gives us the anti-bonding region. Clearly, the bonding region is much higher, much larger than the anti-bonding region, clearly showing that the benzene is very strongly bound to the copper oxide surface. So we wanted to know now then, how does this benzene behave when we have got a benzene ring adsorbed on the surface already? Perhaps if we put the second benzene or third benzene, what is it that we are going to observe? Let's have a look. So let us assume that the benzene which is already adsorbed is B180 adsorbed, yeah? And then we have the B2, which we would like to adsorb on top of it or sidewise. So there could be several cases, but we looked into only 3 cases. These 3 cases are, number 1. So on the first model, we suppose this is the one benzene ring, which is already adsorbed on the surface. The second benzene ring is, we put it on exactly on top of each other. So every carbon atom is on top of the other carbon atom. This is case number 1. Case 2, we rotated the second benzene ring by 60 degrees, and we call it as the top 60 degree. In the third case, we put the benzene ring side by side on the copper oxide surface. Now let us have a look. What did we see when we optimized these structures? So in the optimized structure, in the first case, we saw that the benzene ring, the second benzene ring was repelled. Yeah, this is, and we have seen that similar phenomenon in previously in one of our papers published in 2011, that when we put this, similar kind of benzene rings over top of each other, because the side head-to-head interaction of the pi orbital, there could be repulsion. So this is the same thing we observed here. And the distance between these 2 benzene ring is 3.694 angstrom, which is quite close to actually graphite. Yeah, the distance between graphene layers of the graphite, which is 3.35 angstrom. Now, when it comes to third model, for example, we saw that the second benzene again formed a slanted geometry, and it formed a strong chemical bond with the surface. But in case 2, we see something very interesting, and this is that the second benzene molecule actually forms bond with the, with the first benzene ring, which is already adsorbed on the surface. So these are the top views of these systems. So based on this initial structure, initial calculations, we thought that, yeah, benzene could actually self-assembly, and we could reproduce some the same observations that the experimental colleagues have found. Now, these are the molecules observed, these are the calculated, final geometries. We also calculated the adsorption energy, and we found that this molecule in this system, the benzene molecules are most stable, followed by this one and then this one. And if we look into this molecule, it's pretty clear why the molecule was less stable over the surface. The reason being the electron density available for this benzene molecule is now shared with another one, leading to the weakening of the bond between carbon and copper. So this is the one reason why. But then to look into it in further detail, we analyzed the partial density states. So this is the partial density state for carbon atom in benzene, and this is the carbon atom on in this molecule in the gas phase, and this is the d orbital signature of the copper in copper oxide. Now, based on how these signatures have moved after the molecules have adsorbed on the surface, it could give us a very clear idea of the, the interesting chemical bonding that has been occurring on these surfaces. So now this is for the case 2. We can see these are the d orbital signature of the copper ion, and this is for the p orbital signature of these carbon atoms. And we did the same thing for the benzene molecules, and we found that actually the p orbital signature, the intensity of the p orbital signatures in this case is quite higher than here. And to quantify this, we also calculated the area under curve, between these regions where we believe, because of this overlapping occurring between the d orbital signatures and the p orbital signature, maybe represent the chemical bonding. So we calculated the area under this curve, and we found that in this case it is much lower as compared to this one, as you can clearly see. So this shows why the the benzene molecule are more stable in this case and less stable here. But then this is on 2 molecules. How about if we have a third benzene molecule on the surface? What happens then? So we took these 2 models and started to put the third molecule, and we found that after optimization, for example, when the third molecule was put close to it, it just formed bond with the surface. And if we put on top of the another third molecule on top of the this model, we saw that there was repulsion between them. Similarly, we observed for the other model. But when we took the benzene molecule again and we did something like the top 60 model, we slightly rotated the benzene molecule, then we found that there is not the third benzene molecule also started to form bond with the second benzene molecule. And we observed a molecule like this. So this is the, the probable molecule that we have been thinking might have been observed by the experimentalist. Now, what is the probable mechanism? Why is it that benzene is self-assembling in this case? So we have been thinking about this, and we proposed that this might be because of a free radical-like reaction mechanism occurring on the surface. Let us assume this is the benzene molecule, and this is the surface. So when benzene forms the bond with the copper ions on the surface, basically these carbon atoms are involved, and this results in the in the 2 other electrons are left behind. These electrons could actually rearrange. When you bring the second benzene molecule close to each other, there will be relocalization of the electrons, leading to the formation of the a self-assembled benzene structure like this. So we thought this is probably because of a free radical-like reaction mechanism. Now, based on this, I thought that perhaps we have answered all the questions that we have asked at the beginning of this this part of the talk. So we asked why benzene self-assembles on the copper oxide surface. With this, there were 2 related questions. The first one was, how is the interaction of benzene different on the copper 1,1 surface as compared to copper oxide 1,1 surface? And the second question was, how does benzene behave when there is already 1 or 2 benzene molecules? Now, in the first question, we saw that actually benzene adopts a slanted geometry on the copper oxide surface, but in the other case, it is parallel to the surface, and benzene forms a stronger bond on the copper oxide surface. How does benzene behave on when there's other benzene molecules? We see that actually benzene molecule start to self-assemble. So the presence of oxygen in copper oxide actually initiate self-assembly in benzene. This is what we thought happened. Now, if you'd be interested, please have a look at this recently published paper of ours. Now, in this talk, I tried to show you some examples of my own work, 2 examples of the adsorption of atoms, clusters, and molecule on cluster catalyst surfaces or surfaces in general. Now, in both of this work, we used experimental results to guide us in performing modeling studies, which I thought was very powerful. And using theoretical techniques, we were able to understand the fundamental interactions that at the interface between atoms, molecules, clusters on the catalyst surface. And these studies have also helped us in understanding the probable mechanism of the formation of these new materials. So I hope I have been able to convince you that theoretical techniques could be quite powerful in understanding these new materials. Now, at the end, I would like to thank all my collaborators with whom I have been actively working recently. Thanks to my students who have been working with me for the last 2.5 years here. And also thanks to EPSRC for giving me computational time in HPC Midland Plus, recently in Cyrus. Also, I have been using Archer for all this work, and Supercomputer Wales, which is in collaboration with Dave Willock at Cardiff University. And thank you for listening to me. Thank you very much indeed.
Thank you very much, Aaron, for a really interesting talk. If you'd like to put your questions in the Q&A, I will read them to Aaron and we will get them answered. I think that picture was taken a while ago now, Aaron, on the end of the slides.
Sorry, yeah, I can't go back now.
No, it was just, I think it was your group.
Oh, I see.
If you could put your questions in the Q&A box, someone's asked for the recording. The recording will go up on the Catalysis Hub website within a couple of days. Just give us time to process it and we will get it up so you can access the recording from our webinar. Are there any questions for Aaron on the work, or did he explain it so well that everybody understood it perfectly? Yes, so Jamal, as I said, we will put the recording up on the Catalysis Hub website. So if you check there in a few days, it should be there. I think everyone's being very shy with their questions. Oh, no, we have one coming out. In the first project, Aaron, this is from Kushagra. Why did you put the copper atom in the bulk? What reason?
Oh, as I said in the beginning of the talk, so experimentalist colleagues, they gave us three, I have to go through like this. These three conditions, right, where the copper is either, an distorted octahedral or square planar, square pyramidal environment. Now, to reproduce this, we thought, this could be one good model, because maybe during the experiment, copper has gone into the framework. So that's the reason why we put the copper ion on the cerium surface by substituting one of the cerium atoms, and of course creating an oxygen vacancy so that it has got a 2+ state. And when we did this in the bulk, we thought that maybe in the bulk, if we do the same procedure, it might create the this distorted octahedral or square pyramidal geometry. So that's the reason why we did this calculation. I hope I answered this question. Thank you.
Thank you very much, Aaron. I think Mike has a question. Mike?
Yes, nice to talk, Aaron. Nice to see you.
Thank you. Very nice to see you.
Yeah, nice to see you too. You kind of dismissed the flat bonding between two benzene molecules, saying it was physisorption, weak, and so forth. And yet the actual numbers for binding energy you come up with are actually not that small, it seems to me.
Oh,
I think it was something like -1.2, was it, EV or something like that?
Yeah, just a moment, yeah. You mean here? Can you see my screen?
Yeah.
I can, yes. So, yes,
Even here?
case one, the binding was -1.4 EV. That seems
pretty
strong to me.
Say it again, sorry.
That seems relatively strong to me.
Yeah, it is strong actually, but then the reason why we did not take into this anymore is because we saw that actually in case 2, there's a self-assembly that is occurring. We thought that we'll take this model and start to look into it. And of course, we did perform some calculations by putting another benzene on this system. But what happened was that they either formed bond with the surface and created the same slanted geometry, but it was not able to reproduce a self-assembly structure. That is the reason why we thought it'll be good to take case 2 or case 3.
Yes, I mean, I guess it's a bit difficult to say it's not physisorption in the sense that that binding energy is a binding energy for 6 bonds or something like that, is it?
It is between
Effectively,
yeah, one bond.
so per carbon, it's only a small number.
Yeah, but yeah, definitely this is not physisorption. So this is chemisorption. Definitely, it's a very strong bond here.
Right.
Yeah.
Okay. All right. Thank you.
Thank you.
We have a question from Takashi Toyo, who asks, in the copper Syria system, is it possible to substitute the Syria sites?
Yes, we did actually. For example, where is it? Just a moment. Here. So you see in this model on the surface, we substituted one of the cerium ions with copper atom. And then we also created an oxygen vacancy because in order to give us copper 2 oxidation state. Yeah. So we did perform this calculation as well. But, you know, while we were able to reproduce the square planar geometry, but it was not, you know, square pyramidal, and the bond between copper and oxygen was only one type. But an experimentalists have shown that there are 2 kinds of bond. So of course we performed this calculation, but we were not able to reproduce what experimentalists have observed.
Okay, that's interesting. Amir is asking what temperature and pressure were required for the C6H6 absorption on the copper oxide surface, sorry.
Oh, that's an interesting question. Because for us, when I perform this density functional theory calculation, as you know, these are all gas phase calculations, 0 Kelvin. So we are not talking here about temperature and pressure. Yeah.
Do you have any experimental correlation or?
Yeah, I mean, in terms of the the polymer that we found, I think it is very similar to what the experimentalists have been thinking. Yeah.
Thank you. Are there any more questions from the audience? I can't see any coming in. As I say, the recording of the webinar and all the previous webinars will be up on our website. And we have another webinar coming up on the 8th of February about sonoelectrocatalysis. So I hope you will join us there. If you go to our website, you can register. And all that leaves me to do is to thank Aaron for a very excellent talk. There's a few thanks coming in on the chat, Aaron, to say very good talk. So thank you very much, Aaron, for coming to speak to us or to speak to your computer screen. And I hope to see more of this work soon.
Yeah, thank you so much, everybody. Thank you, Josie.
I will